uh, in any sort of vibration analysis, they break everything down into signs, like sine and cosine waves. You see that wave analysis they do for, vibrating bridges to see if maybe the earthquake's going to shake at the right frequency to knock it down, or they do circuit analysis, or they do voice analysis, break your voice up into all these different components to see what makes your voice sound really good. All those things have been done in terms of sine and cosine. And here's what we have. Since sine and cosine are functions, all right, sine of theta and cosine theta, we can plot their graph, right? The idea is you give me an angle, I give you a value for the cosine function. You give me another angle, I'll give you another value for the cosine function. Since it has exactly one output to every input, it's called a function, just out of algebra. We can catch them. And here's a neat way to do it, is to use the unit circle. There's a nice website called Math is Fun that has a real good moving illustration that's better than I can do here. I'll put it up in a second. But there's the unit circle, so it goes 1 unit in every direction. And you think of making a table, right? That's how you plot functions in algebra. We put x and figure out y, put x and figure out y. Then we put in theta and output y equals sine of theta. So I might start, what happens if I put in theta equals 0? That means the terminal ray coincides with the initial ray at 0, and it goes to this point here with the coordinates 1, 0. And the second coordinate is sine, so I get sine is 0, right? Now the next special angle I know is 30 degrees, about a third of a right angle, somewhere in here. I drop a perpendicular here, and I find out this is a square root 3 over 2, 1/2, 1 triangle. And so this point has coordinates square root 3 over 2, half. And I showed you the picture of the whole unit circle. We can fill this whole thing out. If I go out at 45 degrees, everybody saw the picture I had up here? This point had coordinates square root 2 over 2. If you want to memorize that for the test, you're welcome to memorize that. I like to just think of the picture and make this whatever you prefer. This one is 1/2 square root 3 over 2 coming off that picture. And this one, of course, if you have a 90-degree angle, you get to the point 0, 1. Then it starts coming down in the same way. Here's 2 pi over 3. By the way, we like to plot these in radians, is the popular way. It turns out to be more useful in applications. This point at 2 pi over 3 has coordinates -1/2 square root 3 over 2, which if you look over here, same coordinate was here, just with x negative, right? Because it's now 60-degree angle up this way instead of 60 degrees up that way. This one is minus square root 2 over 2 plus square root 2 over 2. Again, all these are just exactly the coordinates you had over here, except with the negative x coordinate, right? Negative square root 3 over 2 plus 1/2, and then minus 1, 0. And you keep going. Minus square root 3. Now here it's the same coordinates again, except with both of them negative. And then over here in the last coordinate, here's 0, -1. In the last quadrant, you get the x coordinate positive and the y coordinate negative. So this one would be 1/2 minus root 3 over 2. So here's our famous circle. Oops. Time I get to the end of this already, my writing's starting to go. So it's on the table. All right, so I put in all these angles. Here's a pi over 6 here, and then the y coordinate, the sine is 1/2. Here's pi over 4 on the y coordinate is square root 2 over 2. Here's pi over 3 for this angle, 60 degrees. And I get square root 3 over 2. At pi over 2, 90 degrees. sine is 1, the y-coordinate is 1, and then I go back down the same way, square root of 3 over 2 over 2, 1/2, and y-coordinate back to 0 at pi. So here's 2 pi over 3, 3 pi over 4, all the special angles within. And with your calculator, of course, you can fill in all the spots between these. And then, of course, that all takes me 0 to pi. Now I can keep going around here and I get the same coordinates, but negative. So if I now continue with theta versus y equals sine theta, let's not fill all of them in, but that's 7 pi over 6. I'm now around to this angle, and now it's both of them negative, and so I get minus a half here, and it's just right minus this one, and it 5 pi over 4. Now it's just minus this one, minus square root of 2 over 2, and so on, all the way down until I get to 2 pi. It's back to, right, it's a whole rotation. I get back to sine y is the sine theta is the y coordinate is 0. Now I can plot this. This is the fun part, is to plot it over on the side here. And I plot theta versus y equals sine theta, and here's 1. So I noticed the biggest y coordinate I got was 1, and the smallest was minus 1. At 3 pi over 2, it's minus 1. And so this actually only goes between plus and minus 1 for the y values. But I plot this one, oops, not that one, 0, 0. Pi over 6, a half, halfway up. Pi over 4, square root of 2 over 2. Pi over 3, square root of 3 over 2. Pi over 2, 1. And then it goes down in the same way, square root of 3 over 2, square root of 2 over 2, 1/2, 0. So it comes down like this. Got pi. And then it does the same coordinates but negative over here. So it goes like this. Goes down to negative 1 at 3 pi over 2. And it's back to 0 at 2 pi. And if you take your calculator, the graphing calculator, it can do all the points in between, right? It doesn't need special angles, so it'll take the sine of all the coordinates in between. And what you find is you get a graph like this. It's a nice smooth curve that goes through those points. And then what happens after 2 pi? You can keep going, right? You can take bigger angles than a whole rotation. You go around to, for instance, 13 pi over 6, and you start getting a half again. 9 pi over 4, you get over 2. So if you keep going, you get the same points, right? Because it's got the same terminal rate. So this actually goes on forever. Hopefully it was like the song that doesn't end. And that's the graph of y equals the sine of theta. We call that a sine wave because it goes on forever with a repeating pattern. Right? It's a sine function. So a wave is a repeating function that goes on forever. And we notice that it repeats every 2 pi units. So it's called a sine wave. It's a sine function. That repeats. And since the repeating length is 2 pi, we say it has period 2 pi. So 4 pi, it finishes another wave, another period, and 6 pi another period, and so forth. Okay. Now, how would I graph cosine, do you think?
Just taking the x coordinates.
Yeah, it does exactly the same thing. If you look at it, the x coordinates are doing exactly the same thing if you just start here. 0, let's see, if you start here, 0, a half, Square root 2 over 2, 1, right? I'm looking at the x coordinates. It gives me exactly the same coordinates here if I just start at negative pi over 2, negative 90 degrees. And so at negative pi over 2, it's here when sine is minus 1. And it comes up in exactly the same way to 1. And it's equal to 1 when sine is 0. And then it starts doing, right, the x coordinates do the same thing here. It starts coming down from the way and goes through here. They're both equal to square root 2 over 2 at this point. So you get exactly the same shape. A cosine function has exactly the same shape as a sine function. It's just shifted over. And here's y equals cosine x. Because the x coordinates are doing exactly the same thing, just 90 degrees phase shift, we call it, back. So we actually call them both sine waves, even though this one's a cosine function, because it's the same shape. Now here's the graphic that I told you from Math is Fun. There's lots of neat math sites for trigonometry. You might try Purple Math or some of those other ones too. Move this over to the main screen here. Uh-oh, it stopped, huh? It was going. Oops, shoot. Just lost it, didn't I? There we go. And then we move the camera over online. So you can see it does a nice job. This is just what I was doing over there, right? As the angle goes around like this, you plot the y coordinate here, and it makes that sine wave. This one is not scaled with the axes the same, so it looks a little more compacted this way than I did. But I think accurate if you scale the axes equally, but this one's certainly more accurate for plotting points. All right, so there's how you plot a sine wave, kind of neat. And they're showing you down below a common thing if you're an engineer. If you take differential equations, for instance, at this place, here's a illustration here. When you put a mass on a spring, and an ideal spring, they call it a Hooke's law spring. It goes up and down in time. The displacement, if this is the time axis, the displacement as a function of time is actually a nice sine wave for an ideal spring. In fact, in practice, it gradually damps out. There's a little bit of damping in there, and an undamped ideal spring would do that. So lots of fun graphics online. I didn't get when I was a student. All right. There's the plot of sine, there's the plot of cosine. And here's the two of them together. What's up, but I guess I can't. So the cosine is just 90 degrees back, or pi over 2 units back from the sine. And as you can see, it's most common to plot these in radians. And so here's from 0 to 2 pi, the sine function. It looks exactly like from minus 2 pi to 0, and exactly like minus 4 pi to minus 2 pi, and from 2 pi to 4 pi, if we plotted it, just doesn't. Right. So those are the graphs. And then what happens is in practice is you don't tend ever to get just the sine function. You get something very similar. Practice. Whoever gets a electronic circuit or something that repeats its, I mean, this is the current in your alternating current or something, that repeats exactly every 2 pi seconds, right? Nobody gets that. What you get is a wave like this that repeats with some other period, and we can figure out exactly how to plot those with just a little bit of review from algebra. I want to spend most of the time today on getting some review in, so that you're thinking of those, but it'll give you a short thing on here. Just the first problems are where they squish it a little bit. Now, from algebra, you just hold on to those two pictures in your mind. Recall that one graph of y equals, in here, a number times f of x, a f of x, is the graph of y equals f of x, an arbitrary function, it doesn't matter what it is, stretched or compacted, depending on whether a is an absolute value greater than 1 or less than, or between 0 and 1, by a factor of absolute value of a. So if a is 2, it's twice as tall, right? If a is a half, it's compacted to be half as tall. And then, if it's negative, it makes all the y coordinates negative from what they were, so it's upside down over the x-axis. So it's flipped upside down over the x-axis. If a is less than 0. There's a stretch or shrink by a factor of absolute value of a and possibly a flip if a is negative. Then the graph of y equals f of ax. If you put the a on the inside of the parentheses instead of on the outside, it does something in the x direction. It's that of the graph of y equals f of x stretched horizontally. That's to put up here vertically. I multiply with every y coordinate by a, right? If f of x was 2 and a is 3, then it's 2 times 3 is 6. It's 3 times as tall. This was vertically on the first one. The graph in this case is that of y equals f of x stretched or compacted horizontally. Depending on whether a is an absolute value greater than 1 or less than 1. It's 1, it does nothing. By a factor of not absolute value of a, but can you guess? This is where you just kind of have to think about what it's doing. 1 over absolute value of a. So right here, if f of x was 2 and I multiply by 3, it's 3 times as tall, right? I get 6. But here, if x is 2 and I put in a equals 3, I get something else. I get f of 6. And what happens is x only has to be 1 over a times as big to put in the same number and get the same y value out. So if x has to be 1 over a times as big to get the same y value, then you're compacting it by 1 over a, right? X only has to be 1 over a times as big to get the same y value. That's why it's compacted now. It said if a is bigger than 1 and stretched if a is less than 1, the absolute value. And then, of course, if you replace x by minus x, then it changes all the x coordinates and flips it around the y-axis. So now it's flipped horizontally over the y-axis if a is less than 0. This is all algebra. This is not trigonometry, but we're going to apply it to our trigonometry graphs that we just did. So suppose I wanted to do this one. Example, sketch the graph of y equals minus 2 times the sine of x. How could I do that? How could I do that? It's easy, actually. Think about it. I know what the sine function looks like, right? There's less that moving there. It looks like this. I won't graph them on the same scale this time. Goes on forever. It's a wave. By the way, if you just have a string and you put a jolt in it like that, and it travels down the spring, they call that a pulse. So a moving jump in a function is called a pulse, but one that repeats over and over and moves down the string is a wave. So you have traveling waves like that in engineering. vibrations and so forth. How sound travels through the air. It's the pressure variation in the air. All right, and you can break it up into components, each of which is a sine wave, and people do interesting things with that. All right. So y equals minus 2 sine x. Here's y equals sine x. Suppose we recall that it goes all the way up, all the way down, back to where it started, between 0 and 2 pi, and between plus and minus 1. So what does y equals 2 sine x look like? Forget the minus for a minute. That just doubles every y coordinate, right? If I plot y equals 2 sine x, doubles every y coordinate. So when y is 0 before, I get 2 times 0, and it's still 0. When y was 1, now y is twice as big, it's 2. And when y is 0, it's back to 0. When y is minus 1, I still have more room. It gets down to minus 2, and so forth. And then it's back to 0. And so if you double every y coordinate, it just stretches it twice as far over the x-axis, but then it comes back to 0 in the same places. So there's y equals 2 sine x. I can't read. It's twice as tall, stretched, right, about the x-axis. Now, what does y equal minus 2 sine x look like? That just changes all these y coordinates to negative. So it's this one flipped upside down. It goes down to minus 2, back through 0 in the same spot. And where this one's minus 2, this one's plus 2. And it goes like that. So it's stretched by a factor of 2 and flipped upside down. There's y equals minus 2 sine x, right? Any questions on that one? Now let's try another one. So they ask you to sketch y equal sine of a half x. What does that do to the graph? According to my prescription B here, or 2, it's stretched or shrunk horizontally by a factor of 1 over a half. So this one here I should have written down. Stretched vertically by a factor of 2 and flip upside down. Multiplied by negative 2. This one, according to my prescription that I wrote, I'm going to stretch horizontally by a factor of 1 over whatever multiplies. It's 1 over a half, which is 2. So this is going to make it twice as wide. And there's no flip since A is positive. And if you think about it, that's exactly what you want. X has to be twice as big now to put the same number into the sine function and get y. So you get the same y out if you make x twice as big. That means you stretch it twice as far from the y-axis. So if I have y equals sine x again, right, here's 2 pi, here's 4 pi, 0, minus 2 pi, plus or minus 1. There's y equals sine x. Now instead of a vertical stretch, it's a horizontal stretch by a factor of 2. I have 1 over a for the horizontal stretch, which means that it completes one period in 4 pi instead of 2 pi. It goes up to 1 here, back down to here, back down here. It looks something like that. And so it's just pulled twice as far out y, but it's the same height, right? We didn't change the y coordinates. Y equals sine 1/2 x is this one with twice the period. Repeats every 4 pi units instead of every 2 pi units. Still goes through 0, 0 because we stretched it around the y-axis. Here's theta versus y. And I should point out on these graphs, what's typical is once you get the graph down, y equals sine theta, you usually consider these things, oh, let's plot y versus x. And so x is now the angle, and then plot these x and y now, and say it's y equals sine x I'm plotting. You can call the variable, independent variable theta or x or whatever you want, but this is the angle, and here's the sine of the angle. It's just more convenient to use x and y than to use theta and y once you know it. And finally, this will be the last one, then we gotta do review the rest of the time. Suppose I asked you to sketch y equals minus a half sine, I'm sorry, minus 2 sine of the plus 1/2 x. What does this do? It does both those things, right? It has the stretch by a factor of 2 and flip upside down for the y coordinate because of the minus 2 out front. But it has a stretch by a factor of 2 and don't flip horizontally because of the factor of 1/2 inside. So now it's going to be twice as tall and twice as stretched out. Here's the sine function. Pi minus 2 pi 1 minus 1. If I make every coordinate twice as tall, so it goes up to 2, and then I flip it upside down, just do it in pieces here. First, I'll do the, see my dots. This is y equals minus 2 sine x, where I just do the y part. It's now twice as tall and flipped upside down. Right? And then I can do the horizontal stretch by a factor of 2 and stretch it twice as far out. And all I do is I change the period from 2 pi to 4 pi. So I go down to here. Let's see, 2 pi, and then draw far enough for 4 pi. 5. So this one completes 2 periods, and the red one will only complete 1 period. Let's see it. 2 pi, it should go back through here, and then like, so instead of crossing a pi, it crosses a 2 pi. Instead of completing a period at 2 pi, completes a period at 4 pi. And it's just, here's y equals minus 2 sine. So the idea is like the one-man band picture, right? You got the accordion and the drums and the keyboard. You're kind of thinking like this, all this stuff. What a mess. We're gonna learn an easier way than being a one-man band to sketch these soon. There's any questions on the basic graph? So this is the algebra way to sketch those things, and it leads into a easier way. Or notice I'm already saying, here's how I sketch it. I just know what its period is, and I know how tall it is. It's twice as tall, and you don't have to be a one-man band. You can just say, well, I'll make it go between plus and minus 2 because its amplitude is 2, as we say, it's twice as tall. And you make a period 4 pi, so you repeat every 4 pi units. That's a whole lot easier than thinking stretch and stretch. And also, we're going to add to this shifting it over the plane. It's not necessarily right along the x-axis. We want to move it around. So we'll do that next time. I just suggest that you look at 6.1, number 1. That's all we want to do for now. And then I'll pick this up next week. So try looking at those. Be familiar with these stretches, and then we'll do the shifts next time, which is also an algebra technique translated over. Okay. Rest of the period, we want to talk about what can we. Like I said, I'll be here later today, and I've got office hours tomorrow. Any problems so far, or I can pick a few if you.
I have a couple.
Okay.
Can we start off with question 14, I believe?
Yes. And you don't have to stick to these either, by the way. You can certainly do any homework, anything that might be fair game for the test. 14, if cotangent theta equals 2, and theta is in quadrant 2, excuse me. Find the other trig functions. Oh, you picked one of the hardest ones. Find all 6 trig functions. This is one of the things to know when you know a value of one trig function in a quadrant, you know them all, right? But the tangent and the cotangent are the hardest ones. Here's what you do when you're given a cotangent or a tangent. There are actually other ways. I think the book doesn't quite do it exactly the same way. I like to do it this way. I write it as a quotient. Whatever, that's a whole number, I just write it as a quotient anyway. And then I rewrite it by dividing by the root sum square of those two numbers. 2 squared plus 1 squared from the quotient is square root of 5. So I'll divide top and bottom by square root of 5. But remember what that does for me? It gives me a point on the unit circle. The idea is that this is a point on the terminal ray here, or minus the terminal ray, 2 to 1. So this could be y and this could be x on the terminal ray, 1 by 2. Or the terminal ray could be the opposite direction. But see, that's not on the unit circle. The unit circle is this little thing out here that only goes with 1, right? In order to evaluate the 6 trig functions, I need the point on the terminal ray that's on the unit circle. Then I've got all 6 trig functions, right? It's that one or that one. Which one is it? Quadrant 3, that's where you need the quadrant. So I need this point right here. How do I find it? The way you find it is you divide this one and this one by the root sum square, and it always puts you a point on the unit circle. This is now y and x, a point on the unit circle. This one right here, 1 over square root of 5. 2 over square root of 5. But there's another one, right, that has the same ratio, right? Cotangent is, oh, I put y over y and x. It says an x and y because it's cotangent. Sorry. I have to redraw. Tangent. Here's the unit circle. And it should be x is 2, y is 1 on the terminal ray. That's right, this way we get to do it twice. Or it could be the opposite direction, but it's on this line in order to have that cotangent. But we want these 2 points on the unit circle to be able to figure all the trig functions. So this one, if you divide by the root sum square, has coordinates 2 over square root of 5 and 1 over square root of 5, dividing by the root sum square. Or you can get the same ratio by taking negative of each of these. Minus 2 over square root of 5, minus 1 over square root of 5. It still has cotangent equal to 2. And this could be the x coordinate, and this could be the y coordinate. That's what this one right here. You find the 2 points on the unit circle that are in ratio 2 to 1 when you take x over y. And there they are, and that's it. You can see from the line, there's no other terminal rays that can give you that cotangent. Now, I throw one out that's in the wrong quadrant, right? Because the quadrants are counterclockwise, starting in with x and y both positive. 1, 2, 3, 4. If I tell you it's in quadrant 2, then I made a mistake on the exam, right? Because here x is negative, y is positive, x over y will be a negative. Yeah, but so this is correct the way it is. This is the point on the unit circle I want. And now, because I know x and y immediately, I know all 6 trig functions, right? The sine of theta is the y coordinate, is minus 1 over square root of 5. The cosine of theta is the x coordinate, is minus 2 over square root of 5. The tangent, I don't even need the unit circle. If you can't figure out this unit circle, you've got one saving grace to get a point or two, right? Remember, the tangent is the reciprocal of the cotangent. I think this is the easiest way to do it. You can also do x, y over x, but why not just turn this one upside down and say cotangent is 2, then tangent is reciprocal, 1/2, right? Cotangent was already given, that was 2. And then these, secant and cosecant, are reciprocal of cosine and sine, right? So secant of whatever angle it is, I don't even know what angle it is, right? It's got these coordinates, but I don't need to. I just turn these upside down. So this is minus square root of 5 over 2. And cosecant theta is minus square root of 5 over 1, or just minus square root of 5. Here's one reason people in higher mathematics like to leave these not rationalized. Rationalized is good for algebra, so you can look at it and see if it's the same number, right? I told you before. But 1 over square root 2 and square root 2 over 2, are those equal? They don't look equal. When you've done a lot of mathematics, you recognize immediately, you can multiply this one top and bottom by square root 2. Oh, yeah, it is, square root 2 and 2. They are equal, but even though they don't look the same. So rationalizing is just so that when they're equal, they will look the same. But, you know, if you know that game, then leave them like this, because look how easy it is to just turn these upside down now. If it started with it here, if I would have written this as minus 2 square root 5 over 5, and flip that upside down, there's nothing wrong with that. It's just extra work. You have to cancel the square root 5 back out to get this simpler form. So I like to just leave the square root 5. As long as they don't simplify, I like to leave them like that. And so do most higher mathematics people who are used to doing this all the time. Easier to write and easier to flip upside down. There's the 6 trig functions for that one, yeah.
On the exam, are you gonna care if it's rationalized or not? Like, because on some of these questions, like based on your answer key, like some of them were rationalized and some of them.
Yeah, the answer is if it can be simplified by rationalizing it, you have to. If it doesn't, then, right? So don't write this 2 over square root 2. That's a square root. Yeah, don't write 2 over square root 2 unrationalized, because that simplifies, right? You can write 2 as square root 2 square root 2. And then cancel these. And this is a whole lot easier, right, than this. You can't leave this one unrationalized because it's simplified. But if you have 2 over square root 3, you can leave it like that because there's nothing to cancel. If I rationalize that, I just have to write it as 2 square root 3 over 3. That's not simpler. So this one's okay because it doesn't simplify, but this one's not because it simplifies. Right?
Oh.
So you can leave them unrationalized whenever there's nothing to cancel.
And then also, while we're on that subject, when I was working on the review, there were some questions that I got wrong because of the rounding, like decimal point wise.
Oh,
So, like,
yes, yeah.
Because like at one point I got 10.6 on it, like the first part of the answer, and you got 10.7.
Yeah.
But then it got all the rest of my answers wrong because like
Yeah.
the answer was like 10.57 or something, so it should have been 10.6.
Somebody else asked me about that already too, which is a really excellent question on the first exam, because it always comes up. And I meant to say something and forgot. Yeah, on these ones where there's rounding, if you get 10.6 and I have 10.7, that's usually 100%. Sometimes you made an error multiplying or something, but usually what happened is you made a calculation in a different order than I did. And when you do these rounded numbers in a different order, you can get numbers that are off in the last place by 1 or 2. If it's off by 3 in the last place with just one multiplication or division, then you made a mistake somewhere in your division or multiplication. But yeah, you will commonly get off in the last digit by 1 or 2. Doing it completely right if you just do it in a different order. Like, for instance, if I say solve the triangle and this is whatever, a 47-degree angle and this is 5, and I say solve it, and you find this side first and I find this side first, and then you use this side to find this side with the Pythagorean theorem, or you find this side using the Pythagorean theorem. Well, you about half the time get something that's off in the last place. Yeah.
So it won't be counted.
So it won't be counted wrong. No, you just did it in different order. It's perfectly good. Yeah.
Thank you.
Yeah. So don't worry when you're off just 1 or 2 in the last place. Yeah. One's around. Be careful on the test that some people put their decimal answers. If I say exact answer, and the answer is square root 3 over 2, leave it like this. This is the exact answer, right? Oh, let's say square root 3. This is the exact answer. But if I say round to 2 decimal places, then I want 1.73. So if I say round, make sure here's square root 3 looks like this. And since the next place is 4 or less, I would say this rounds to 1.73. So if I say round to 2 decimal places, I want this number. If I say exact answer, I want this number. Right? Simple.
We do 24.
Yeah. Oh, good, yeah. That's a very important, because I can never do all the examples in class. One of the things I wanted to do today was make sure I did all the ones that are on here that we haven't talked about previously in class. gear problem. This is a wonderful problem that I like to do, but ask for time to do it earlier. A gear of radius 15 centimeters, again, since it's applied, I'll draw a picture, is used to turn a gear of 8 centimeters. It takes too long to draw all the teeth, so I'll just say, these actually have teeth that mesh, right? So they turn without slipping is the idea. And here's a gear of radius 8 centimeters. If the larger gear turns through 120 degrees, which is a little more than 90, here's a 120-degree turn. From what angle does a smaller gear turn? How about that? This is an applied problem that I really like to do because it's the kind of thing that happens in real life, right? This one is going to turn some angle. What is that? Well, here's what happens is since they turn without slipping, they turn through the same arc length, S. So S is, if I call this radius 1 and this theta 1 for the big gear, I can call this radius 2 and call this theta 2, right? So S is equal to R1 theta 1 is also equal to R2 theta 2 since they turn without slipping, right? Arc length is R times theta, no matter which gear you do, right? And so this is the equation you immediately write down. You don't need the S in the middle, just R1 theta 1 equals R2 theta 2. Now this S equals R theta applies only in radians, right? So you think, oh, I have to use radians. But actually, once you write it this way, if it's not in radians, it still works because these both convert together. If you convert these both to degrees, you multiply by 180 over pi on both sides. So this actually works without the S in the middle. It works in either degrees of radians. So it doesn't matter. But if you leave the S in there, then you need. So I write that equation down. Now I put in everything I know. I know R1, theta 1, and R2. I just put them in. R1 is 15 times 120 degrees. We can put it in radians if you want. Equals R2, which is 8 times theta 2 that I want to find. Evidently, theta 2 is 15 times 120 degrees over 8. Nothing more to it than that. Once you've done one of these, what you realize is I just take the angle of bigger, turn by the bigger gear and multiply it by the ratio of the radii. 15. That's how the smaller is 15/8 as far. So that's what this relationship implies. And let's see what that is in the calculator.
1,800. And then when you divide it, it's 225.
225, okay. Theta 2. However, there's actually technically something wrong on this that I won't mark on the exam if you do it. What's wrong with that?
10 degrees.
No, I didn't say you can put it in radians. So you can put, if I don't say which one, you can put it in either. Okay.
It's negative.
Oh, awesome. Yeah. It's negative because this one turns counterclockwise, a positive 100. It forces this one to turn clockwise, and so it's a negative angle. Technically, well, I'd like to write it this way, but technically the angle, if you put plus or minus, I'll count it. I'm not going to worry about which direction. It turns through 225 degrees, right? But technically it's clockwise. We'll put that.
Thank you.
We go over 29, please.
Yeah. Isn't that a fun problem? I really teach you something about applications. Two cities have the same longitude. Again.
29.
29.
29. Okay. Oh, I forgot this one.
Oh, that one was.
Oh, yeah, this one. 14. Okay. Yeah. Okay. 29. Two cities have the same longitude. Again, since it's an applied problem, I'll try drawing a picture. I'm starting to say. Longitude is here's lines of equal longitude. It's how many degrees you are going around the equator. And then basketball Earth there. Latitude of one city is 9 degrees. So let's take it up to here. That's a small angle. 9.00. Latitude is how far up from the equator you are. We're headed have a GPS on your phone. I have one on mine. I use it for geocaching. And then city B is 30 degrees. Here's 30 degrees. A little more than 3 times as far. North, so I drew it up since it's north, and then latitude south or down from the equator. Assume that the radius of the Earth is 3,960 miles, right? So here's 3,960. Find the distance between the two cities. So if this is city A right here at 9 degrees, and then due north of it, because it's on the same line of longitude, is city B. We're asking how far between them, meaning how far would you have to walk along the Earth? Now, once you draw it, maybe you see exactly what it is. What is it? It's the arc length around a circle, right? So it's r theta, where r is 3,960 base of the Earth, miles. Keep the units to remind you how to write the answer. You don't want to put feet. And then times, it's 21 degrees, and I get the wrong answer. Here's the other reason you write the units. What's wrong with that? That looks like a, yeah, S equals R theta only works in radians. You multiply it by pi radians for every 180 degrees. Now the degrees cancel. The radians go at any time because they're unitless, and I've got miles. Good. So there's the other reason to write the units. I need 3,960 times 21 times pi over 180. Hopefully I'll get the answer in the back. Don't forget you've got blue caret to get the pi, lots of digits. I get 1,382 miles to the nearest mile. If I multiply by pi over 180, I'd get about 57 times that amount. That's more than the radius of that's more than the radius of the Earth is probably more than the diameter of the Earth is.
Back was 1,451.
Oh. It up. Oh, I multiply by 20. If you fat finger it, this always comes out. Yeah, thank you. 60, 21. All right, here's the other thing on the test I tell people, always check your answers. Yeah, now I get 1451. I hate about the new phones. I can never guess. I always touch it in the wrong spot or pushing the wrong number. They're too tiny. That big a finger, do it. What some of these professional wrestlers do with a phone. But he's expert on all the rest of them. Those are really good questions.
Can we do 31?
Yeah,
I think this is a Pythagorean identity one.
okay.
I think I was getting confused on it.
So I said use the cofunction identity. So this is a cofunction identity. The cosecant of 35 degrees is the secant of what? And the cofunction identity said this. Remember the cofunction identities? In any triangle, I have theta. What's this angle here? It's a complementary angle, right? 90 minus theta. Consequently, if I call this B and A and C, I notice that the cosine of theta is adjacent over hypotenuse is B over C. So this is, well, for 90 minus theta is the opposite of the hypotenuse to this angle, right? So it's the sine of that angle. And so cosine of B over C is sine of theta is sine of 90 minus theta. Similarly, the sine of theta is opposite over hypotenuse is A over C, is the cosine of the complementary angle over here, right? A over C is the adjacent over the hypotenuse to this angle. Right, and then the similar to the tangent, the cotangent and the tangent. Cotangent of this angle is this one over this one is B over A, is the tangent of this one, adjacent, opposite over adjacent, tangent 90 minus theta. The tangent of theta is similarly cotangent of 90 minus theta. Secant similarly, let's do cosecant first matter, but cosecant theta is secant of 90 minus theta. And so every cofunction is equal to the function and its complementary angle. We call these the cofunction identities. They just come out of this little triangle here. They're true in the unit circle for any angle, but it's easier to visualize it just for the triangle, so I usually do that for cofunction identities. And there's 6 of them. We can take out these middle parts from the proof. Every cofunction is equal to its original function at 90 minus theta. The cosine and the sine go together in pairs. The cotangent and the tangent and the cosecant and the secant. So I say, what's the cosecant of 35 degrees? Is the secant of 90 minus 35 degrees. All right, that's 55 degrees. So it's a really easy question, actually. Have to use the cofunction identity, or it's hard. It's hardest actually in radians. Maybe I'll give you a radians problem here. For instance, what is the tangent of pi over 5 is equal to the cotangent of what? About that. These things in degrees and radians become that the tangent of theta is the cotangent not of 90 minus theta, but of pi over 2 minus theta. So in radians, just change 90 degrees to pi over 2. And so what goes in here is pi over 2 minus pi over 5. Whatever angle's here, it's subtract from a 90 degrees angle, pi over 2. And what makes this harder is you have to do the fractions, right? Or the quotients, I guess. You put them over a common denominator, multiply this one top and bottom by this denominator, call it 5 pi over 10. Apply this one top and bottom by that denominator, call it minus 2 pi over 10. Now you can subtract them, same denominator, right? 5 pi less 2 pi is 3 pi over 10. That's what goes in this. So it's harder in radians. You have to do these little over common denominator stuff. Cofunction identities are not a big topic, but I might give you one of those. That's why it's on the practice test.
We do 15. I don't remember what was weird about it, but there was something strange about it.
Yeah, okay.
88 works, but two degrees.
That's right.
Other applied problems, I'll draw a picture. A golfer. He's 5-foot tall flag or pin. At angle of elevation, that's the angle up from horizontal. Two degrees. Suppose it's exact. Find the distance to the flag, assuming horizontal ground and a vertical flag. How far does the golfer have to hit the ball? You know whether you have the trusty 9-iron or the big wood to hit it all that way. Oh, it's such a frustrating game. First trying to learn that with my friend, we couldn't hit the ball and we were down at the playground trying to hit the ball and then all of a sudden he got a hold of it once and it flew clear out of the playground. Wanged up in somebody's house. We had no idea it could go so far. So we ran away, of course. All right, so what's the distance here? To the flag, if it's 5 foot tall and this little tiny angle of 2 degrees. Once you draw it, maybe you can see what to do, right?
So when we were setting it up, we were using tangent and everything like that. And the only way we got it to work was once we found the missing angle and used that angle instead. But we couldn't figure out why it wouldn't work when we did 2 degrees.
Ah, that's weird. You can use
Yes.
whatever angle you want, yeah. So you made an 88-degree angle over here, is that right?
Yes, sir.
Ah, I would just use the angle that's there and say, I'm given 2 numbers in a right triangle. I can find everything in there. What I want is this one. That's why you draw the picture. So I want a trig relation that relates this side, and this angle. And so tangent or cotangent relates these 3. Cotangent is in the calculus. I'll choose tangent and say tangent is 2 degrees. This angle is its opposite side over the adjacent side is 5 over d. And so I multiply both sides by d and get d tangent 2 degrees equals 5. Maybe it was the division that was the problem. And then divide by tangent 2 degrees, or you can just take reciprocals here and then multiply by 5. There's lots of ways to do this algebraically. Divide by tangent 2 degrees, get d equals 5 divided by tangent 2 degrees. This isn't degree. Gives me 143. Since 5 was measured in feet, this will also be in feet. That's gonna be a 7. Depends on your. And we just.
I don't remember what we did, but I think
I know, we
Yeah.
divided by 5 instead.
divided by 5.
That's exactly what we did.
Okay, okay. Yeah, so you need a
Okay.
cotangent. Okay. All right, any others that you want to look at? I'll tell you what I am gonna ask you, just to say at least one is important. Is one where you solve a right triangle, so it could be one like this, or it could be one like, let's say solve the triangle.
The 32.
Yeah, I was just looking at that one. Yeah, so we can do 32. Here's what I could give you as a problem like this. Here's a picture. May not even give you a picture, but I just tell you some of the sides. That's what some of the homework. 15, 40 degrees, so it's not a special triangle. This one's 50 degrees. A and B. And solve. I said find each side. I'll probably say find the other angle also. But I'll just say in this one, solve the triangle. What I do is, since I have 2 independent pieces of information, an angle and a side, I know I can solve this, and I just relate these 2 things I know to one I don't. And when I have one angle, I always just do the easy thing and say find the other angle. So this is opposite side A, I'll call this alpha. And this is the hypotenuse, I'll call this C. This is opposite side B, so I'll call this beta. And step 1, I'll use the complementary angles theorem as easiest and just say alpha is 90 minus the 40 that I have for the other angle is 50 degrees immediately. Now I'm stuck with trigonometry. I try and relate any 2 pieces of information, these 2 or this one, by trig relation to any other side I want. Let's find B. And say this one over this one is the opposite of the hypotenuse to 40 degrees. So we'll say sine of 40 degrees is opposite B, I don't know, over 15C that I do know. Right? So I related 2 numbers I know to B that I want to find. Multiply both sides by 15, I get 15 sine 40 degrees equals B. B must be Okay, thank you, 9.64. And if I say, place to round it, oh, I said round to 4 decimal places, what have I got at 4 decimal places?
418.
Okay, so there it is, 1, 2, 3, 4 places right of the decimal point is 4 decimal place accuracy. Now, finally, for step 3, I can use trigonometry again if I want. I could say that cosine of 40 degrees is this one over this one. Use trig. There's nothing wrong with that. If you do that, I'll give you 100%. But what most people like to do, because it's easy, is go to the Pythagorean theorem. You got two sides of a right triangle. The Pythagorean theorem gives you the square root of the third side. And I've already got that number on my screen, so it's real convenient. I'll simply say for step 3, I need C, right? I've got C. I need A. So A being a leg is the square root of C squared minus B squared by the Pythagorean theorem. Solved for A is the square root of 15 squared minus 9.6418 squared. And then I can take advantage of my calculator's abilities here to avoid maybe an error. I can actually carry this with all the digits. I don't have to worry about mistyping them because I can say second x squared invokes the square root function, right? Square root is the inverse of the square. And then 1, 5, x squared button if you have one. Otherwise, you put hat 2. Minus. And instead of putting this one, I can push second and the little, what has it above it? I think it's the minus sign on the TI-84. That's done different. It says A and S on top. This will bring up whatever was the last number on your screen, right? So I can push second ands to bring up this number, 9.6418, with all its digits, including there's usually one off the display that's not even seen. And then push x squared on this, and then close my parenthesis on some calculators I need it, and push enter. And that'll do it, right? This closes the square root parenthesis. So on the screen up here is square root parenthesis, 15 squared minus ands squared, close parenthesis. So you're trying to get this on the screen is the idea. And what do I get? Or you can type in this number. There's nothing wrong with that if you don't do what I just did. Last problem.
11.4907.
Thank you. And then on these problems, I always suggest you do the sanity check. Does this make sense? The hypotenuse would be the longest side. That's C. 15 is bigger than both of these, right? Do the angles add up to 90 degrees, 40 and 50? Sure they do. So probably it's right. Right? So right angle there. Okay. So I'm going to ask you a problem to solve it. What's sort of fundamental?
Will you do 33 just because that's not on the answer key?
Oh, okay. Yeah. I'm liable to ask him. Surprised I didn't put that on there. 33A. What I want is the cosecant 17 pi over 6. If I ask you to, this is a special angle. How do I know it's a special angle? A special angle is a multiple of pi over 6 or pi over 4, right? So this is 17 times pi over 6. Immediately, it's a special angle, right? Multiple of pi over 6 or pi over 4, 30 degrees or 45 degrees. So I know I can do this one exactly. What I'll do for this one is, what I can do for any angle is do it on the unit circle. So I take 17 pi over 6 and break out first any whole rotations. And so I write it as, I notice this is between 1 and 2 whole rotations, right? One whole rotation would be 2 pi, which is 12 pi over 6. 2 rotations would be 4 pi, which is 24 pi over 6. Quick multiplication. So I can pull out 2 pi, which is 12 pi over 6. And that leaves me 5 pi over 6. I pull out a rotation plus 5 pi over 6. All right. Now can I pull out a straight angle? That would be pi. Well, this is only 5/6 pi. There's not a straight angle to pull out. But I can pull out a right angle because this is bigger than pi over 2, right? 5/6 pi is bigger than a half pi. So I'll pull out a pi over 2, which I can also call 3 pi over 6. Right, this is 5 pi over 6 is 3 pi over 6 plus 2 pi over 6. Now this one is pi over 2. That's pulled at a right angle. And 2 pi over 6 is also known as pi over 3. So I'll say this is 2 pi, a whole rotation, plus pi over 2, a right angle. If you want, you can convert this to degrees immediately. There's nothing wrong with that. Sometimes it's easier, but in the long run, you want to be able to do these. Plus pi over 3. There we go. Thinking in degrees, that's a rotation, that's a 90-degree angle, and that's a 60-degree angle. And you can draw it pretty easily, right? Here's 2 pi. Since it's positive, I go counterclockwise. Pi over 2 is a right angle. And pi over 3 is 2/3 of a right angle. That's 60 degrees, so there's pi over 3. Break this quadrant into 3 parts. There's my terminal ray. And now I can even just picture this in my mind sometimes once I figure out all these quotients. I drop a perpendicular or I memorize that unit circle picture. And I observe that if this is pi over 3, that leaves a 60-degree angle, and this leaves pi over 6, a 30-degree angle, right? For the reference angle. That's a 30-degree angle. I know all 3 sides of the right triangle that fits in the unit circle. This is 1 because it's a unit circle. This is a half, and this is square root of 3 over 2. Now I know the coordinates of the point are negative square root of 3 over 2 since I went left, plus a half since I went up. And the cosecant, recall, is 1 over y. That's why it was defined. So it's 1 over a half. It's just 2. Exactly. Now, if you put that in your calculator, a lot of these calculators will do these exactly also, by the way. So technically, your calculator can get that exactly. But on the test, I might ask you, show the unit circle instructions. Because, like I say, there are lots of calculators today, not the TI-84, but you put in 17 pi over 6 using the pi button, not a decimal constant. It will tell you the exact answer. And actually, in this one, because it came out an exponential number, decimal. Well, maybe on the test, I'll say show the unit circle. Well, sounds like it's time to go. Bring me any more questions you have. If you have, like I said, a few minutes after, if somebody wants to do one.
What relationship?
Oh, and it's on the syllabus, but the one today is gonna be in room 113 at the end of the hall, right? And the one tomorrow. Anyway, some of them are in 103, right, next door here, and some of them are 113.
12:30.
Yeah, 12:30. Okay.
We're meeting in the library again.
Thank you, everyone.